Welcome! In this session, we'll tackle LeetCode problem number 1975, number of ways to separate numbers. This problem challenges us to determine how to split a string of digits into valid sequences. It's an interesting exercise in dynamic programming and string manipulation. Let's dive in and explore the best approaches. The problem asks us to determine how many ways we can split a given string of digits, s, into one or more non-empty substrings. Each of these substrings must represent a positive integer without leading zeros. Additionally, the integers formed from these substrings must appear in a non-decreasing order, meaning each integer should be greater than or equal to the one before it. Because the number of ways to split the string can become very large, the result must be returned modulo 10 to the power of 9 plus 7. The input to the problem is a single string s composed of digits from 1 to 9, and the output is an integer representing the total number of valid ways to split the string according to these rules. To better understand the problem, let's consider some examples. In the first example, the input string is s equals 327. The output is 2 because there are two valid ways to split the string. The first way is 327, where 3 is less than or equal to 27. The second way is to treat the entire string as a single number, 327, which is valid because it has no leading zeros. Both splits meet the criteria, so the result is 2. In contrast, for s equals 094, the output is 0 because the string contains a leading 0, making it impossible to form any valid splits. Another example is s equals 1234, where the output is 8. This is because there are 8 valid ways to split the string while maintaining the required conditions. These include splitting it into individual digits, like 1, 2, 3, 4, and grouping substrings like 1, 2, 34 or 12, 34. In all cases, the substrings represent positive integers with no leading zeros, and their values are in non-decreasing order. This example highlights how the number of possible splits can grow quickly as the length of the string increases. The 8 valid splits for s equals 1234 continue with options like 1, 234, 12, 3, 4, and even treating the entire string as one number, 1234. All of these satisfy the problem's conditions. The constraints specify that the string length can be as large as 3500, which means we need an efficient algorithm to handle such cases. Key edge cases to consider include strings with leading zeros, which are always invalid, and strings where the digits are strictly decreasing, which might result in no valid splits at all. On the other hand, single-digit strings always have exactly one valid split. Understanding these constraints and edge cases is crucial for designing an optimal solution. To solve the problem of determining the number of ways to separate a string of digits into valid substrings that form a strictly increasing sequence, there are two main criteria we need to satisfy. First, every substring must represent a positive integer, meaning it cannot begin with a 0. Second, the integers formed by these substrings must strictly increase from left to right. While the problem may seem straightforward at first glance, the real challenge lies in efficiently exploring all possible ways to split the string and verifying that the resulting sequence satisfies these conditions. Without the right strategy, this task can quickly become computationally expensive due to the vast number of potential splits in a long string. To address this, we'll explore various approaches and trade-offs to arrive at an optimal solution. One possible approach is to use brute force, where we generate every possible way to split the string into non-empty substrings and check if each split satisfies the strictly increasing condition. This can be done using recursion or backtracking to explore all partition options. For each split, we verify whether the sequence of integers formed is valid. However, there's a significant drawback. Generating all possible partitions results in an exponential time complexity of 2 to the power of n. This is because we consider every possible split point in the string, and the number of splits grows exponentially with the length of the string. This makes the brute force approach infeasible for larger inputs, such as strings with more than 20 digits. To overcome these limitations, we can use a more efficient solution by leveraging dynamic programming with pre-computation. This optimized approach allows us to systematically compute valid splits while reducing redundant calculations. Key observations include recognizing that comparing substrings lexicographically is sufficient to determine their order, avoiding the need for integer conversions. Additionally, by pre-computing results for repeated substring comparisons, we can significantly speed up our solution. Ultimately, this reduces the problem to finding valid partitions ending at each position in the string. The dynamic programming approach can be formulated as follows. We define a DP table dp I, j, where dp I, j represents the number of ways to split the substring s0 I plus 1, such that the last segment of the split is s, j, I plus 1, and all numbers in the split are strictly increasing. To compute dp I, j, we iterate over all possible previous partition points and check whether s, k, j is less than s, j, I plus 1. By using pre-computed results for substring comparisons, we can optimize this step. The base case is straightforward. dp0, 0 is initialized to 1, as the first character alone forms a valid substring. In terms of complexity, the time complexity is O(n squared, accounting for the dp table and substring comparisons, while the space complexity is also O(n squared, due to the size of the dp table. This approach is both efficient and scalable, making it suitable for large input sizes, even for strings with up to 3,500 characters. By leveraging the power of dynamic programming and pre-computation, we achieve a polynomial time solution, which is a significant improvement over the infeasibility of brute force methods. When comparing the different strategies, each comes with its own trade-offs. The brute force method is simple to implement but becomes computationally prohibitive as the input size grows. Greedy algorithms, which might seem appealing, are not applicable here because the decision to split depends on future substrings, making it impossible to make local decisions without considering the entire sequence. The dynamic programming approach, on the other hand, strikes the right balance between efficiency and scalability. By pre-computing substring comparisons and leveraging overlapping subproblems in the dp table, we avoid redundant work and handle large inputs effectively. This problem underscores the importance of optimizing operations like substring comparisons and designing algorithms that minimize unnecessary calculations. While the dynamic programming solution requires careful implementation, its reduced time complexity makes it well-suited for real-world constraints. Overall, this approach demonstrates how advanced techniques like pre-computation and DP can transform a seemingly intractable problem into one that is computationally manageable. In this problem, we need to determine the number of ways to split a given string of digits into non-empty substrings that represent strictly increasing positive integers. The key challenge lies in ensuring that the integers adhere to this increasing order constraint, which can be complex given the numerous possible splits. To tackle this, we use a dynamic programming approach, which provides a systematic way to explore all valid splits while avoiding redundant calculations. One of the central insights here is the use of prefix comparisons to efficiently check whether one substring is greater than another. This eliminates the need to repeatedly compare substrings during the computation. Additionally, we optimize our solution by pruning invalid cases early on, such as substrings with leading zeros or splits that do not satisfy the increasing order condition. These insights form the foundation of the algorithm we'll develop. To implement the solution, we rely on a few key data structures. First, we use a dp table, where each entry dp I, j represents whether the substring ending at index j can form a valid sequence with the previous substring ending at index I. This allows us to systematically build valid sequences. Second, to streamline comparisons, we pre-compute a prefix comparison array, which tells us whether one substring is less than or greater than another. This avoids redundant work during the main computation. Finally, since the result can grow very large, we use modular arithmetic to ensure that our result fits within constraints, specifically modulo 10⁻9 plus 7. The algorithm begins with initialization, where we set up the dp table and pre-compute substring relationships. The base case involves validating substrings starting from the first character. For instance, if a substring from S0 to Sj has no leading zeros, it can initialize the dp table with a valid count. The core of the algorithm lies in filling the dp table. For each possible ending index j, we iterate over all potential starting indices I that are less than j. The goal is to check whether the current substring, Sij plus 1, is greater than the previous substring, Sk of I, where k is an earlier starting index. To perform this comparison efficiently, we rely on the pre-computed prefix comparison array. If the condition holds, we accumulate the number of valid ways from dp k I1 into dp I j. This ensures that all valid sequences ending at j are accounted for. Once the table is populated, the final step is to compute the result. We sum up all valid sequences ending at any position in the last row of the DP table and return the result modulo 10⁻9 plus 7 to handle large values. This structured approach ensures that we systematically explore all valid splits while maintaining efficiency. Let's look at a concrete example with the string s equals 1234. We start by marking the first substring, 1, as valid, setting dp 0, 0 equals 1. Next, for the substring 12, we check if it is greater than 1. Since it is, we update dp 0, 1 equals 1. Similarly, for 123, we find that it is greater than both 12 and 1, so we update the relevant entries in the dp table to account for these sequences. This process continues until all substrings are processed. We optimize this by skipping invalid substrings, such as those with leading zeros, and by using the pre-computed comparison array to quickly evaluate whether substrings meet the increasing order requirement. To further improve efficiency, we can reduce the space complexity by using a rolling array, which reuses only the last row of the DP table. In terms of complexity, the time requirement is approximately O(n cubed, dominated by substring comparisons, while the space complexity can be reduced from O(n squared to O(n) with optimizations. This balances correctness with efficiency, making the solution both robust and practical. To solve the problem, we start by defining a constant, mod, which will be used later to ensure our results fit within the required constraints by taking modulo 10 to the power of 9 plus 7. Next, we define the function number of combinations within the solution class, which takes the string number as input. The length of this string is stored in n. To handle edge cases immediately, we check if the input string starts with 0. If it does, we return 0 since numbers cannot begin with leading zeros. We then initialize a two-dimensional array LCP, which stands for longest common prefix. This matrix helps us compare substrings efficiently later on. The matrix is initialized with zeros and has dimensions, n plus 1 x, n plus 1. After initialization, we fill the LCP matrix by iterating backwards through the string. Whenever characters at positions I and j match, we compute the longest common prefix by referencing the diagonal value LCP, I plus 1, j plus 1, and adding 1. This matrix is critical for optimizing substring comparisons in the next steps. To compare two substrings efficiently, we define a helper function called compare. This function takes the starting indices and the length of two substrings and uses the LCP matrix to determine if one substring is less than or equal to the other. If the common prefix length meets or exceeds the required length, the substrings are deemed equal. Otherwise, the function compares the characters immediately following the common prefix to determine the order. We then set up a dynamic programming table, DP, as a two-dimensional array initialized to zeros. Here, dp I, j, will store the number of ways to partition the substring number, j plus 1, such that the last partition starts at index I. We initialize the first row of the table by setting dp 0, I, to 1 for all valid I, since any prefix of the string can form a valid partition starting at the beginning. Next, we iterate through the string starting from the second character. For each starting index I, we calculate a cumulative sum to track the number of valid partitions. For every ending index j greater than or equal to I, we first check if the substring starting at I and ending at j begins with 0. If it does, we set dp I, j, to 0 since such a partition is invalid. Otherwise, we calculate the length of the current partition and determine the starting index of the previous partition. If the previous partition exists and satisfies the order condition using the compare function, we update dp I, j, by adding the value from the previous partition. Additionally, we add the cumulative sum of valid partitions to ensure all possibilities are accounted for. Finally, we take the modulo with mod to keep the value within bounds. After populating the DP table, the result is obtained by summing up all valid partitions that end at the last character of the string. We return this sum modulo mod as the final answer. Here, we start by defining our solution class and setting up a constant for the modulo value, which is used later to prevent overflow during calculations. The main method, number of combinations, takes a string number as input, which represents the number we are analyzing. First, we check if the string starts with a 0, as numbers starting with 0 are invalid for this problem. If it does, we immediately return 0. Next, we pre-compute the longest common prefix, or LCP, matrix. This matrix helps us efficiently compare substrings later on. The LCP matrix is built by iterating backward through the string. For each pair of indices, if the characters match, we increment the LCP value based on the next diagonal value, essentially extending the common prefix length. This pre-processing step ensures that we can compare substrings in constant time during the main logic of the algorithm. Now, we define the helper method compare, which uses the LCP matrix to determine if one substring is less than or equal to another. By leveraging the pre-computed LCP values, we can efficiently compare two substrings without redundantly iterating through them. Next, we initialize our dynamic programming array, DP, which tracks the number of valid ways to partition the string ending at each position. Initially, for the first row, all positions are set to 1, as single-digit numbers are always valid. Then, we begin iterating over the string with two nested loops. The outer loop handles the starting index of a substring, while the inner loop processes the ending index. For each substring, we first check if it starts with 0. If it does, we skip it since leading zeros make the substring invalid. Otherwise, we calculate its length and determine the starting index of the preceding substring to compare. If the previous substring exists and satisfies the comparison criteria, we update the current DP value based on the DP value of the previous partition. This ensures that the number of ways is accumulated correctly. Next, we handle the cumulative sum to account for all valid partitions up to the current index. If the previous starting index is valid, we add the corresponding DP value to the cumulative sum, ensuring we include all possible ways to partition the string. The current DP value is then updated with the cumulative sum, modulo the constant mod, to avoid overflow. Finally, after processing all substrings, we calculate the total result by summing up all valid partitions that end at the last index of the string. This gives the total number of ways to partition the input string into valid numbers. The result is returned as the output of the method, completing the implementation. This approach efficiently handles the problem's constraints by leveraging dynamic programming and the pre-computed LCP matrix for substring comparisons. In this example, the input number is 327. Since the first digit is not 0, we proceed with the solution. First, we determine the length of the number, which is 3, and initialize two key data structures, the LCP matrix and the DP matrix. The LCP matrix, or longest common prefix matrix, is a 4x4 matrix filled with zeros, while the DP matrix, which will store dynamic programming results, is a 3x3 matrix also initialized with zeros. Next, we populate the LCP matrix by comparing substrings starting at different indices. For instance, the last characters match, so LCP 2, 2 is set to 1. Similarly, the substrings 27 foot and 27 match, resulting in LCP 1, 1 equals 2. Finally, the entire input matches itself, giving us LCP 0, 0 equals 3. All other entries remain 0, as no additional substrings match. These values allow us to determine the overlap between substrings efficiently. Now we move to populating the DP matrix to calculate the number of valid partitions using dynamic programming. First, the base case is applied, any prefix can start a partition, so all entries in the first row of the DP matrix are set to 1. After this initialization, the DP matrix becomes 1, 1, 1, 0, 0, 0, 0, 0, 0. Next, for I equals 1, we examine all j values where j equals I. For j equals 1, we compare the substring 3 with 2. Since 3 is greater than 2, we set DP 1, 1 equal to DP 0, 0, which is 1. However, for j equals 2, the substring 3 is less than 27, so this partition is skipped. The updated matrix becomes 1, 1, 1, 0, 1, 0, 0, 0, 0. Finally, for I equals 2, we only check j equals 2. Here, the substring 27 foot is greater than 7, so DP 2, 2 is set to DP 1, 1, which is 1. The final DP matrix is 1, 1, 1, 0, 1, 0, 0, 0, 1. To calculate the result, we sum the last column of the DP matrix, which gives 1 plus 0 plus 1 equals 2. Thus, there are two valid ways to partition the number. In this second example, the input number is 1234. With the first digit not being 0, we proceed to the solution. The length of the number is 4, so we initialize an LCP matrix as a 5 by 5 matrix of zeros and a DP matrix as a 4 by 4 matrix of zeros. Next, we populate the LCP matrix by comparing substrings starting at different indices. For example, the last characters match, so LCP 3, 3 is set to 1. Similarly, the substrings 34-foot match, resulting in LCP 2, 2 equals 2, while longer substrings like 234 and 1234 also match, giving LCP 1, 1 equals 3 and LCP 0, 0 equals 4. All other entries remain 0, as no other substrings overlap. This matrix allows us to efficiently calculate the overlap between substrings of different lengths. Next, we populate the DP matrix to determine the number of valid partitions. The base case remains the same, any prefix can start a partition, so all entries in the first row of the DP matrix are set to 1. As a result, the matrix becomes 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. For I equals 1, we examine all j values where j equals I. Comparing the substring 1 with 2, 23, and 234, we find that 1 is smaller in each case, so no valid partitions are added to the DP matrix. Similarly, for I equals 2 and I equals 3, we find that no valid partitions exist because the substrings starting at these indices are also smaller than subsequent substrings. Consequently, the DP matrix does not change further. To calculate the result, we sum the last column of the DP matrix, which gives 1 plus 0 plus 0 plus 0 equals 1. Thus, there is only one valid way to partition the number. Finally, we consider the example where the input number is 101. Since the first digit is not 0, we proceed with the solution. The data structure initialization follows the same pattern as before. However, this example is unique because the string contains a 0. Substrings that start with 0 are not valid partitions, which immediately limits our possibilities. As we explore the DP matrix, we find that no valid partitions can be formed due to this restriction. Consequently, the result is 0, indicating that there are no valid ways to partition the number. In analyzing the time complexity, the solution can be divided into several key components. First, we have the pre-computation of the LCP matrix. This matrix stores the lengths of the longest common prefixes between all pairs of substrings in the input string number. To compute this matrix, we iterate over all possible pairs of indices, I, j, in reverse order, where both I and j range from 0 to n1. For each pair, we perform constant time operations like checking if two characters match and referencing the next entry in the matrix. As a result, this pre-computation step has a time complexity of O, n squared. Next comes the process of filling the DP table. The DP table has dimensions nxn, and we iterate over all pairs of starting and ending indices, I, j, such that I equals j. This gives us O, n squared, pairs. For each pair, we use the compare function to check substring relations, which takes O, 1, time due to the pre-computed LCP matrix. Additionally, we update cumulative sums and values in the DP table, which also takes O, 1, time per operation. Altogether, filling the DP table also results in a time complexity of O, n squared. The final step in the solution involves summing the values in the last column of the DP table. Since this operation only requires iterating through n elements, it runs in O, n, time. When we combine all of these steps, the overall time complexity of the solution becomes O, n squared plus n, which simplifies to O, n squared. Now let's consider the space complexity. The memory usage of the solution largely comes from the LCP matrix and the DP table. The LCP matrix is a 2D array of size, n plus 1 is x, n plus 1, so its space requirement is O, open parenthesis n plus 1 close parenthesis squared, which simplifies to O, n squared. Similarly, the DP table is a 2D array of size nxn, contributing another O, n squared, to the space complexity. In addition to the LCP matrix and DP table, the solution uses a few temporary variables such as cumulative, length, and various loop indices. These require constant space, or O(1). When we combine all of these components, the total space complexity is dominated by the LCP matrix and DP table, resulting in O(n²). To highlight the efficiency of this approach, let's compare it with a brute force method. A naive solution would involve generating all possible partitions of the string number and then checking the validity of each partition. Given a string of length n, there are approximately 2(n1) possible partitions. Validating each partition, for example, to ensure non-decreasing order, would take O(n) time. This makes the total time complexity of a brute force approach O(2 to the power of n*n), which is exponential and impractical for large input sizes. The optimized approach, by contrast, leverages dynamic programming and the pre-computed LCP matrix to achieve significant improvements. The LCP matrix enables substring comparisons to be performed in O(1) time, while the DP table ensures that intermediate results are reused, avoiding redundant calculations. Together, these optimizations reduce the time complexity to O(n²), which is a dramatic improvement over the exponential brute force approach. Now, let's break down the best, average, and worst-case performance of the algorithm. Even in the best case, such as when all the characters in the input string are identical, the algorithm still needs to compute the LCP matrix and fill the DP table, both of which require O(n² time. On average, for typical inputs, the algorithm consistently runs in O(n² time. In the worst case, where the structure of the input string requires processing all possible pairs I, j, the time complexity remains O(n²), as the algorithm is designed to handle these cases efficiently. To mathematically justify the O(n² time complexity, we observe that the algorithm's key operations, computing the LCP matrix, updating the DP table, and performing substring comparisons, are all bounded by the number of pairs I, j, in the string. Since there are at most n² such pairs, and each operation runs in constant time, the overall complexity is proportional to n². This ensures that the total time complexity is O(n²). Similarly, the space complexity is determined by the size of the LCP matrix and DP table, both of which require O(n² space. Thus, the solution achieves a balanced and efficient design with both time and space complexities firmly bounded at O(n²). Here are some common pitfalls to watch out for when solving this problem. First, be cautious about substrings with leading zeros, like O1 foot or 001. These are not valid integers and should be skipped in your logic. Next, ensure that any comparisons between numbers are done numerically, not lexicographically. For instance, while the string 9 is less than 10 lexicographically, numerically, the opposite is true. Always convert substrings to integers before comparing. Another mistake is inefficient substring generation. Naively generating all possible substrings can lead to unnecessary computations, especially with larger strings. Instead, leverage dynamic programming or memoization to streamline your approach. Additionally, don't overlook edge cases. Strings that are empty, contain just one digit, or consist of repeating digits like 1111 can cause issues if not handled properly. Finally, be mindful of large numbers. If a substring represents an integer that exceeds the maximum value for standard data types, your solution might fail. Use data types that can handle arbitrary length integers, like Python's built-in int or Java's big integer, to avoid this issue. When approaching this problem in an interview, it's crucial to start by fully understanding the requirements. The task involves splitting a string into valid integers while adhering to constraints like avoiding leading zeros and handling potential integer overflows. If anything is unclear, don't hesitate to ask clarifying questions. Recognize that this problem involves substring manipulation and numerical comparisons, which are common patterns in backtracking, dynamic programming, and other string-based problems. To simplify the problem, break it down into smaller subproblems. For instance, you can use a dynamic programming table where each entry indicates whether a specific substring is valid. This helps structure the solution efficiently. It's also important to weigh the trade-offs between different approaches. While backtracking may be easier to implement, it often results in inefficiencies. Dynamic programming, though requiring more effort to set up, usually reduces redundant computations and is more optimal for larger inputs. This problem shares similarities with several other problems on LeetCode, making it valuable to study these related questions. For instance, LeetCode number 91, Decode Ways, involves substring manipulation combined with dynamic programming, a pattern you'll also encounter here. LeetCode number 472, Concatenated Words, focuses on splitting strings into valid segments, a concept closely tied to this problem. Similarly, LeetCode number 139, Word Break, challenges you to split a string into valid parts based on a dictionary, which is another variation of the substring manipulation theme. Lastly, LeetCode number 44, Wildcard Matching, involves working with strings under specific constraints, which can help build your string manipulation skills further. Exploring these problems can deepen your understanding and prepare you to handle variations of this challenge in the future. There are several alternative approaches to solve this problem, each with its own trade-offs. Backtracking is a straightforward method where you recursively try all possible splits and validate them as you go. While this approach is simple to implement, it has a high time complexity of 2 to the power of n, making it impractical for larger inputs. It's best suited for smaller cases or as a quick way to validate your understanding of the problem. Dynamic programming is another powerful approach. By using a DP table, you can store the results for valid splits up to each index, reducing redundant calculations. For instance, dp I can represent the number of ways to split the string up to index I. This method is significantly more efficient, with a time complexity of n squared, though it requires additional space for the DP table. Finally, a sliding window approach can be considered if the problem constraints allow. It enables you to focus on substrings of specific lengths, reducing the overhead of generating all possible substrings. However, this method is less flexible and may not handle all edge cases dynamically. Choosing the right approach depends on the input size and constraints provided in the problem. Thank you for joining this session. We've summarized the key points of the problem and its solution. Remember, mastering dynamic programming is a critical skill for tackling complex problems like this one. Stay motivated and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!